We showed that the delta function can be used as a model, a physical model for a sharp blow or an impulse spike. But now we're going to come back to the other motivation behind the delta function. We want a nice way to come up with the transfer function and the Green's function for these equations in general. So what we're going to do is we're always going to come back to this rest condition initial value problem. But this time the driving force is just going to be this delta function, delta of t. Now remember, if we take the Laplace transform of both sides, the delta function was defined so that it gives us a 1. It's just the most convenient way of trying to come up with the transfer function we want. Because of the rest initial conditions, this is always going to generate some polynomial in terms of s in front of the function we want. So the function we want here is going to be given by 1 over that polynomial times 1. This we define as the transfer function. And so what we get here is that our transformed solution is just the transfer function. We want to get the answer, so we need to take the inverse of this. And that is what we call impulse response. Now, impulse response is really, really important for mathematicians, for physicists, for engineers. Engineers in particular like to put an impulse, a spike into an unknown system and see how it responds. And the reason they do that is because the response is going to be how the transfer function behaves. Once you know the transfer function, you don't really care what the differential equation is because you know how it responds. You have that transfer. You've encoded this information about the left-hand side. So finding impulse response is important. So we get the transfer function. That's this h of s. This, the inverse Laplace transform of it would be what we call impulse response. The Green's function we get by saying, okay, we are going to take this Green's function, t and tau. It will be the inverse, where t gets shifted to t minus tau. And then the solution, yp, or the solution is going to be given by convolution. And so, in general, I'll rewind a step, that gives us the Green's function. So the reason we do all of this is that once we know the transfer function, once we know the impulse response, once we know the Green's function, we can come back to any dE with these rest conditions. The solution is just going to be found from convolution, integral 0 to t, and it's always going to be given by this Green's function that we found simply integrating the right-hand side. Done. Case closed. We know everything about this linear differential equation. All we needed to do was study how it behaved under an impulse, see what its response was under the impulse, and then we are finished. That's how engineers, for example, use this in practice. Now we can take a look at specific examples. So for example, let's say y double prime minus y equals the delta function, and we have our rest initial conditions for this second order problem. If we were to take the Laplace transform of this equation, the whole purpose of defining the delta function this way is that it gives it a 1. We'll have s squared minus sy of 0 minus y prime of 0. Each of those is going to be gone. Minus capital Y of s is going to be 1. We'll have s squared minus 1, capital Y of s is 1. So this is what I mentioned. When you have rest initial conditions, you will always get some polynomial in s right in front of your transformed function. You'll get y of s is 1 over s squared minus 1. This right here is the transfer function. Once you've got the transfer function, then the next step is to find what we call impulse response. And so impulse response is basically taking the inverse transform of the transfer function. In this case, it's going to be the inversion of 1 over s squared minus 1. This is the sinh function. So this would be sinh of t. We can call this g of t if we want. The Green's function then just becomes the inverse of that, the impulse response shifted to t minus tau. So it would then be the sinh function at t minus tau. And then we have everything we need to know. Once you have the Green's function, the solution to any y double prime minus y f of t with these rest initial conditions then becomes written as a convolution. It's the convolution of the Green's function, sinh t minus tau, times f of t. Whatever that f of t is, you just plop it in there. This magical Green's function encodes everything you need to know about the left-hand side. It all gets translated into your solution. That's the point. Problems are all solved. Now, of course, you change the left-hand side. This can be changed to anything else you want either. And the beauty of all of this is that it can apply to whatever higher order problem you'd like. It doesn't just have to stop with a second order problem. Remember that we found a Green's function by doing a lot of work for second order problems, but it doesn't have to stop with a second order problem. What we could end up doing is applying it to any order. So as a specific example, here is a fourth order problem. So the fourth order problem we'll take a look at is this. Fourth derivative, 5y double prime plus 4y. Now, this would be a pain if we needed to do this with our other solutions, with our other methods. We didn't even discuss what to do with the standard method. So we'd have rest initial conditions. Now remember, you might say, well, why is it always rest? What happens if we don't have rest? Remember that when we defined the Green's function a while ago, we can always split our problem up into two. One of them will be a driven problem with rest initial conditions. The other one will be a homogeneous problem with non-homogeneous conditions. And that's the beauty of linearity. When you have linearity, you can do this stuff. So it isn't artificial for us to always consider this. We will be able to deal with this. Now, the point is the same. We go ahead, we apply the Laplace transform to both sides. But if we want to solve this problem, we are going to instead say, let's talk about the impulse response. So let's study impulse response. So instead of talking about the f of t on the right side, let's just take the delta, because that's how things are done. We always drive it with an impulse response, see how it responds, and then we generalize that. This is going to give us s to the 4 times y of s. There are going to be several other terms, s cubed, y of 0, s squared, y prime of 0, s y double prime of 0 minus y triple prime of 0. All of those terms are going to be 0 because of the rest initial conditions. We'll have 5s squared y sy of 0, y prime of 0 plus 4 capital Y of s. Again, without the rest initial conditions, this would be a nightmare. But that's why we take advantage of linearity. We split the problem up. We always create rest initial conditions so that we can always take these techniques and solve them. This was a fourth order problem. we see that mirrored with a fourth degree polynomial out front. This is going to get us the transfer function. The transfer function here is always the reciprocal of that polynomial. So this is h of s. This is the transfer function. And it's a fourth order problem. We didn't feel any difference, right? There's no difference. That's the beauty of Laplace transform. We want the impulse response. The impulse response is the inversion of that transfer function. So what we do is we need to invert this reciprocal function. Now, how you do that becomes problematic at times, right? This could be challenging depending on what specific function you've got. Now, in this particular case, this can be factored. This can be factored into 1 over s squared plus 4 times 1 over s squared plus 1. And then we should talk about partial fractions. So in the partial fractions case, what we'll have is that 1 should be as plus b over s squared plus 4, cs plus d s squared plus 1. This ends up giving us a new polynomial that we want to consider. There are many different ways you can tackle this to try to find a, b, c, and d. But basically what ends up happening is you should use convenient test points. The poles of each of these are going to be plus or minus I and plus or minus 2I. So if we pick I, what will happen is that the first term will be 0. The second term is going to give us ci plus d times 3. And that makes life really easy, because what you end up with is a system. So for the imaginary part, we've got nothing on the left and 3c on the right. For the real part, we've got 1 on the left and 3d on the right. So d is a third and c is 0. Now when s is equal to 2i, you're going to have a similar situation. You'll have a 1, 2ai plus b times negative 3, and this term will be 0. That's going to give you something equally easy when you talk about the coefficients. You're going to have a 0 and a 1. So the 0 will be for all the imaginary parts. So you'll find that a is 0, and this will be negative 3b. So b will be negative 1/3. That means your impulse response, you're basically going to have the following. You'll have a negative 1/3, 1 over s squared plus 4, plus a 1/3, 1 over s squared plus 1. Linearity kicks in. You have an inverse transform of 1 over s squared plus 4, 1/3 inverse of 1 over s squared plus 1. You need to put in a 2 upstairs here so that you can get the proper expression down there. So you'll need to put the 2 upstairs and then a 2 downstairs. So this will end up giving you negative 1/6, the sine of 2t, 1/3 the sine of t. And this right here is your impulse response. We can call this g of t. The Green's function is then the impulse response shifted to time t minus tau. Simple matter. T minus tau. What you end up getting is a negative 1/6 sine of 2t minus tau plus 1/3 sine t minus tau. And you're done. So now, if you ever need to solve this same fourth order problem, remember, fourth order problem, this would be normally fairly challenging to deal with when you talk about constructing a Green's function, but you're done. The solution, y of t, is always given by a convolution of the Green's function with this f of t. f of tau, I should say, d tau. If you want to get the specifics in there, it's going to be a convolution integral -1/6 sine of 2t minus tau plus 1/3 sine t minus tau times your f of tau d tau. That's it. You're done. This would have been a horrible nightmare if you had done it otherwise, but once you have the impulse response, game over. You've solved every problem you need.